In this lecture, we will learn about laser amplifier, amplifier gain, amplifier phase shift. Laser amplifier is one of the most important part of getting lasing action. One of the primary conditions for the laser is stimulate emission. We have discussed last time. But after stimulation, amplification is necessary. We will discuss details here. Yes, we have discussed basics of laser in the previous lectures. What are laser? How it can be prepared? What are the basic conditions of obtaining lasing action? After stimulate emission, amplification is an important issue. We'll discuss these things in this lecture. At the end of this lecture, you will be able to learn about amplification of laser, how laser actions taking place, and how a stimulated emission photon converted to lasing action. Yes, before beginning our topic, I've just shown the figure of Charles Stones and their colleague who developed a principle of light amplification by stimulated emission of radiation that is called laser, and they received Nobel Prize in 1954 for this. Many things in this have been left for students as they might learn these things in the previous classes. Even though I have given many details in the last lecture about the interaction of radiation, then pumping, the concept of pumping, concept of population inversion. Pumping means a process to send to create population inversion. Pumping means to send photons from lower level to higher level. Pumping is a process by which we send the electron on excited states. So this excitation can be take place by various methods. One of the most celebrity example is from the light. You can strike light, you can insert light on the system, so the light, a photon is absorbed and move to excited states. But other methods also there, in which electrical discharge, you can discharge through electrical purpose. In this, for helium, neon, and CO2 gases, we use a tube, and in the tube, discharge tube, we apply electrical discharge. But this is one of the most important method, pumping. The another thing which is very important is this resonator. The resonator is shown here. The left of mirror is called total reflector. This mirror on the left hand side, which is dark, is shown, is called resonator. And on the right hand side, where we have used, that is partial transparent mirror, which is used to get laser outside. This total completely is called laser cavity, and this whole system is called optical resonator. So whenever we study or whenever we want to obtain lasing action, we have to keep this your lasing material between the two mirrors. One is full, one is partial, and that arrangement is called Fabry-Perot. In the figure, the functioning of optical resonator is shown. Of course, pumping is not shown here, but normally we have pumping from both the side, or this is covered from all the side for pumping if we want to pump with optical behavior. Now, first we pump the system, so the pumping starts stimulate emission. Here, suppose you pump, and first will start, that is called spontaneous emission, and that spontaneous emission may generate stimulated emission. If it is strike to an atom which is on excited state, it suddenly move to ground state and will give you 2. So here I have shown 2. Now these 2 will again strike to another excited and may give you 4. So 4 may give you 8 and so on. So you will get many stimulate emissions. And the difference between this stimulate emission and spontaneous emission is these stimulate emission are identical in all respects. All the photons are same polarization, same direction, same energy, same frequency. So whenever these moves, this creates, this remote photons creates an amplification. First, you are observing here, this is continuously increasing, then move to this, then from here, some move to back, and again increasing, 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 and finally they move to here and again reflected back. So, in this process, large number of stimulated photons will generate, which continuously move back and forth and create the process of oscillations here. This is the basis by which we get lasing action. In this figure, if you move from top figure to bottom figure, you will observe that everything is giving here one by one. The first figure is showing you the lasing material. Where we pump the system, the pumping is shown in the second. We pump the energy, electrical, optical, or chemical, or whatever the process is. By pumping, they move to excited state. We have shown normal ground state with a faded color and excited state with a high different colors, bright colors. Now, this excitation is called population inversion, and by after this population inversion condition, we observe spontaneous emission. Now, these spontaneous emission we have shown in the third figure. Now, these spontaneous emission may be in many directions. Some are in axial direction, some in outward direction. Those which will outward direction will be lost, but those in the axial direction will survive, and then it will move back and forth in these mirrors, and by this they create intense beam. You can see here the intensity is shown by the bigger, broader curve as compared to the previous one. So this is called laser beam. Whatever we discuss here, it's a part of amplifier. Actually, this is also termed as coherent optical amplifier. Coherence is the most important property of lasing action. Coherence means all the waves, all the photons that we are getting must be coherent, must start at the same time, must end at the same time. There should be no phase variation. It means Suppose two photons are having no phase difference, then it should not be have any phase difference afterwards. Or if they have any phase difference, then it must be constant for the process. The conclusion is phase all the coherent sources are those sources which have either zero phase difference or constant phase difference called coherent amplifier. Now we want here to create coherent light. That light is created by stimulated emission. Now the question is stimulated emission you will get, but how to increase the amplitude for laser? For this we are talking about amplifiers. This is a device. Stimulated emission allow a photon in a given mode to induce an atom in an upper energy level to undergo transition to lower energy. And we have discussed this in the past lecture in detail. Now in the process to emit a clone photon identical photon into the same mode as the initial, that is stimulated emission. Photon have the same direction, same frequency, same polarization. These two photons in turn serve to stimulate emission of two additional photons and so on. While preserving these properties, the result is coherent light amplification. So first you will get 2, then 2 to 4, then 4 to 8 and so on. It's called amplification. And for this amplification we use a certain arrangement where we organize such amplification. Electronic amplifier rely on devices in which small changes in an injected electric current or applied voltage result in large change in the rate of flow of charge carriers, such as electron and hole in a semiconductor field transistor or bipolar field transistor. So electronic amplifier which rely on electric current applied field. However, an essential ingredient for achieving lasing amplification is the presence of greater number of atoms in upper energy level than in lower energy level. That is called condition of population inversion. This is clearly a non-equilibrium situation because normally in the equilibrium condition, system wants to live in ground state, lower state. So if system wants to live in lowest state, the higher state will be less populated. But in this population inversion, we want to create a condition where higher level have more electrons. Achieving such a population inversion requires a source of power to excite. That is called pumping of atom from lower level to higher level. The laser amplifier, an external power source called a pump, excites the active medium which is placed inside the pumping mechanism shown here. This is pumping mechanism, and here we are giving pumping to some place. Here we are having your material. It is called active medium. Now this produces a population inversion and photon interact with atoms when stimulated emission is more prevalent. The medium acts as coherent amplifier, and finally you will get the output. The properties of an ideal coherent amplifier opticoelectronic are displayed here. In a linear system that increases the amplitude of the input signal by a fixed factor called amplifier gain. A sinusoidal input leads to sinusoidal output at the same frequency but larger amplitude. Here that is important, amplitude is increasing. The gain of the ideal amplifier is constant for all frequencies within amplifier spectral bandwidth. The amplifier may impart to the input signal a phase shift that varies linearly with frequency, corresponding to time delay of the output. In this figure, an ideal amplifier shown which is linear. There are two amplifiers shown. In ideal, the input is given and output is given. You can see here this is very small amplitude, but on the right hand side the amplitude is increasing. This probably introducing a linear phase shift. A real amplifier typically has a gain and phase shift than the function of frequency as shown. So in the case of ideal, the input amplitude and output amplitude, some variation is linear. But here the variation is non-linear, increasing, first increasing, then stop. So this can be checked. The gain and phase shift constitutes the amplifier transfer function for a sufficiently high amplitude. Furthermore, the real amplifier may exhibit saturation, a form of nonlinear behavior in which the output amplitude fails to increase proportion to input amplitude. The saturation introduces harmonic component into the output, provided that the amplifier bandwidth is sufficiently broad to pass them. Real amplifier also introduce noise so that randomly fluctuated component is always present at the output, regardless of input. The amplifier may therefore be characterized by the following features: gain, bandwidth, phase shift, power source, and non-linearity of the gain situation. These are the factors used to characterize. A monochromatic optical plane wave traveling in z direction can be given by this equation. And if we have two levels n1 and n2 having different energies, if their energy difference is h nu, the wave is amplified with the gain coefficient yz and undergoes a phase shift phi z per unit length. We proceed to determine expression for gamma nu and phi nu in attenuation. The photon atom interaction is there, and when the atom is in lower state and photon is absorbed, move to a higher state. In a stimulated emission, identical photon is emitted. And these processes lead to attenuation or amplification. The third form of interaction, spontaneous emission, in which the atom in upper state emits photon independently of presence of other photons. Now this is responsible for amplifier noise, but Triple emission gives you identical photons. The probability density that an unexcited atom absorbs a photon and give is given by W here. Here it is shown that the photon flux density phi entering at internal cylinder, incremental cylinder, and excited atom gives phi plus d phi. So move from phi to pi is shown here. Now the amplifier gain is seen to be proportional to population difference n1 minus n2. n1, although n was considered to be positive in the example provided above. The, the derivation is valid whenever the sign of n, whatever the sign of n, either it is higher or lower, in the absence of population inversion. If there is no population inversion, then n2 is less than n1. So is the gain coefficient. The medium will then attenuate, light traveling in z direction in accordance with exponential decrease. However, for the interaction region of total length d, the overall gain of the laser amplifier is defined as the ratio of photon flux density. G nu is equal to exponential of gamma nu t. Because the gain of the resonant frequencies medium is frequency dependent, the medium is dispersive and frequency dependence phase shift must be associated with its gain. The phase shift imparted by the laser amplifier can be determined by considering the interaction of light with matter in terms of electric field rather than photon flux density. We proceed with an alternative approach in which the mathematical properties of causal system are used to determine phase shift. For homogeneous broadened media, the phase shift coefficient is related to the gain coefficient by the Kramer-Koenig relations, so that the knowledge of the gain coefficient at all frequency can be determined. The incremental amplifier represents a physical system. It must be causal. But the real and imaginary part of transfer function of the linear causal system are related by Hilbert transforms. So amplifier phase shift function is determined by gain coefficient. A gain coefficient is known, that is lambda nu, and your phase shift is phi nu, that can be given by this relation. So at resonance, the gain coefficient is maximum and phase shift coefficient is 0. Shown here how this takes place. Laser amplifier, like other amplifier, require an external source of power to provide energy to be added to input signal. The pump supplies this power through mechanisms that excite the electron in the atom, causing them to move from lower to higher atomic energy levels. To achieve amplification, the pump must provide a population inversion on the transition of interest. The mechanics of the pumping often involve the use of ancillary energy level other than those directly involved in amplification process. However, the pumping of atom is more readily achieved. That is again important. Sometimes we assume many other levels also. Here, the rate equation is given. If we consider a schematic energy level diagram shown here, we focus on level 1 and 2. have overall lifetime, that tau 1 and tau 2 respectively, and permitting transitions to lower levels. The lifetime of 2 has two contributions. One associated with decay from 2 to 1, that is called tau to 1, and other tau to 0 associated with decay from 2 to other lower levels. When several modes of decay are possible, these transitions rate is a sum of all other possibilities, transition rates. The rates are inversely proportional to decay times, and reciprocal of, that is the reciprocal of the decay time, must be added. So I am adding here decay time tau 2, which is equal to tau 2 1 and tau 2 0 sum. Here it is shown that the how energy level 1 and 2 together with surrounding higher and lower levels. We are having several levels lower than 1 and higher than 2, and how energy transfer may take place. The rate equation, the rate of increase of population density can be given as like this: dn2 over dt, rate of increase in the second population of n2, is equal to r2 minus r2 upon tau2, n2 over tau2. Similarly, for first population, dn1 over dt is equal to minus r1 minus n1 upon tau1 plus n2 upon tau2. These are called rate equations. In this, N will represent the steady state population difference and in the absence of amplifier addition. The large gain coefficient clearly required large population difference. A large population difference value can be achieved by, we must have large R1 and R2 reactions, long tau 2 but spontaneous, which contribute to tau 2 through tau 1 to 1 must be sufficiently short so as to make radio transmission rate large, and short tau 1 if R1 is less than tau 2 upon tau 1 to R1. So these are the conditions. In this lecture, we have discussed about amplification, how amplification can take place, and why it is needed, and rate equations. Thanks. Thank you. In this lecture, we have learned about population inversion and optical amplifier, and then their equations.